Hello. So this time we will talk about the changeable variable in its general form, or so-called Jacobi factor or Jacobian. So change variables in multiple integrals. First, let's recall in 1D. This is a well-known fact in 1D. Suppose you have an integral of f from a to b, and the transformation x equals gu. You might get integration of function f gu g prime u du, and then the domain is from C to D, where C is where GC equals A and GD equals B. So here you see the tricky part is you have G prime U here as an actual factor. Otherwise, just use substitution. Okay, then in 2D, we have some similar special case, which is known before, that is polar coordinates. Suppose you have x equals r cosine theta, y equals r sine theta. Then the integration of the two-variable function f over a certain domain A over a certain domain R can be transformed into the following form. The domain is transformed to S in its polar coordinate system, and the function is fr cosine theta, fr cosine theta, r sine theta. And then we know we have r d theta. So here you have r as your actual factor. Then a natural question is, what if more generally the transformation we have is an abstract one, g x u v, y is y u v. Do you have some similar formulas as before for polar coordinates or in 1D case? Okay, so the answer you can expect is yes. And before we figure out the actual factor, like here, we would like to first show an example how to transform the domain, which is also very important. So suppose the domain, suppose you have transformation T given as follows to UV. And so the question is, find the image of the square UV. U is between 0 and 1, V is between 0 and 1. Okay, so the solution is pretty straightforward, as well as we know to determine the domain, the image, we only need to determine the image of the boundary. So first, let's consider the UV plane, and with 4 points, 4 vertices, A, B, C, D. This is S, and then the coordinate you have is as follows. And we should keep in mind, so to determine the domain, the fundamental principle is figure out its boundary. The boundary always map to boundary. At least in this course. Okay, then let's figure out what is the image of, for example, AB, interval AB in XY plane. So recall AB in UV plane is parameterized by the V coordinate is 0, so all U is a variable and V is set to be 0. Of course, due to the picture, you see U is between 0 and 1. Okay, then you use the transformation T here. So consider TAB. So what is this set? Since so you plug in V equals 0. What do you have? X now is U squared, and Y, because it's 2UV, so it's just 0. And the condition, and the U is between 0 and 1. Therefore, X is also between 0 and 1. So what do you have is the following piece. Let me use this one. So from 0 to 1, 0. So this is your AB. And in particular, notice in particular, A is mapped to 0, 0 in XY plane. You can just plug in points. Therefore, you have TA here, TB here. Okay, then similarly, let's figure out what is AD. So AD is parameterized by 0V. V is between 0 and 1. And then TAD, you plug in the coordinates. You have Y is also 0, and then X is negative V squared. Therefore, you can draw the picture here. So this is D. This point is D, negative 1, 0. And here, correspondingly, you can draw like this. Okay, next, let's figure out the other two boundary. What is BC? BC, the coordinate is 1V. V is a free variable between 0 and 1. And then the transformation T. X is 1 minus V squared. Y is 2V. If you eliminate V, you get the following equation, quadratic equation. X is 1 minus Y squared divided by 4. So this will be like here. So the intersection is 1, 0. So you might have, and so let's notice that y-intercept is 2, negative 2, and then x-intercept is 1. Therefore, you have this I draw a dash line here, but then because later on you will find we only take a part of it, because this is B. If we take a part of it, I will show you later. Okay, then what is the remaining one, CD? So CD is parameterized by U1, and U is between 0 and 1, and the TCD is x equals U squared minus 1, y equals 2U. So x is y squared divided by 4 minus 1. It's easy to see the x-intercept is still 1, but y-intercept is x-intercept is negative 1, y-intercept is 2 and negative 2. So you may have this one. So I will choose this as solid. Okay, so from this picture, you see these 4 lines. Okay, so let me draw BC. You have 2 choices. Basically, you either go this way, so the red one, yellow one, blue one, and the colorful one gives you the boundary corresponding to this one, or you can choose this one. But that doesn't mean both are your solutions. You need to check one inside the point. For example, let's take a point here, E. So E is 1/2, 1/2. Okay, then check TE. So what is TE? So TEX is 1/2 square minus 1/2 square. Y is 2 times 1/2 times 1/2. So x is 0, y is 1/2. Therefore, the image of E is here. This is TE. Okay, then you see the green part should be on this side, and then your point TC, just this one. Sorry, this is TD. This is TB. Okay, although this example is quite easy, but I will just do it in detail so that you know how to explicitly determine the domain. Okay, now we turn to another topic, how to figure out the actual factor. Next, let's figure out the transformation law. So we do it infinitesimally first, and then by approximate the integral by Riemann sums to generalize the result to its full generality. So suppose you have a very small rectangles here, and let's fix some coordinates. So the lower left corner, let's call it U0, V0, and then this is du, this is dv. Therefore, the point here is u0, v0 plus dv, u0 plus du, v0, u0 plus du, v0 plus dv. So you have 4 corners. And then suppose you have arbitrary transformation t. So recall t just a transformation, x is t1 uv, y is given by t to uv. So the whole transformation like this. Think about the previous example we did, how to write down t in its coordinates. And then the image, you can guess, in general, it might be a curved rectangle. It's close to a rectangle, but not exactly. Okay, then let's denote these points. So for simplicity, here I will change the notation to gamma. Okay, and then here, so this point, so x0, y0, what is x0, y0? This is just gamma u0, v0. And this point, corresponding to this point, therefore, we can write down the coordinates like gamma u0, v. V is v0 plus dv. And this point, is gamma u v, and then this point is gamma u v0. Okay, and then the inside just map to inside one. So next, we want to understand, compare the area. Because of the definition of extra factor, we want to compute the ratio of two areas. Okay, we want to compute this area divided by this area, or the reverse, depending on how you define your extra factor. Okay, this side, so notice the left-hand side is easy. You just, but we need left-hand side, you can compute it easily. So the area equals du times dv. Okay, then we need to figure out the right-hand side. But the right-hand side, as we see, it's curved. We don't know the exact value. However, since we're in calculus class and we assume the original one is infinitesimal, then we can approximate by some small rectangles. So this is your original one. A bad drawing. And then here you take the tangent vector and then you construct this one. So I hope you still remember how to find the most closest rectangle to this one. In other words, how to find the tangent plane to this surface. So we recall. So from the formula, suppose you have gamma u and v. So we can do linear approximation, which equals gamma u0 v0 plus gamma u u0 v0 du plus gamma v u0 v0 dv. That's a linear approximation for u and v, pretty close to u0 v0, and apply to our case. So this is your A, this is B, C, D. Sorry. Yeah, let's call this A, B, C, D. Oh. And then this is your approximation, B prime, C prime, D prime. And recall the coordinate for let me write down coordinate for A, B, C, D. So this is gamma. Let's write down in vector form. Gamma U0 V0, gamma U0 plus DU V0, gamma U0 plus DU V0 plus DV, gamma U0 plus U0 V0 plus dV. Okay, on the other hand, we can compute A prime, B prime, C prime, D prime by linear approximation. So on this side, you have A prime is just A, so it's this one. And what is B prime? B prime should be a linear approximation for B, and apply this formula here. So you have this is approximately equals to gamma U0 V0 plus gamma U U0 V0 and times du, because dv is 0 here. And similarly C prime, let's do D prime first. D prime is gamma U0 V0 plus gamma U, this is the derivative with respect to gamma V times dV, because you don't have du term. And then C will be just like this one. V0 times du plus gamma VU0 V0 times dV. Okay, next your job is to calculate the area. So area of the red part approximately equals to the area for of the blue part. And then the blue part, since it's a parallelogram, so we all know what is the formula. So this equals to, this is equals to, so A B prime, A prime B prime. So here A prime, A equals to A prime cross product A prime D prime. And then since we know the coordinate here, we can just plug in and then compute it. So the left hand side, so A prime B prime, you have gamma U U0 V0 dot du, and cross product gamma V U0 V0 dot dV. Okay, and then you have gamma U U0 V0 cross gamma V U0 V0 and du dV. So that's the area. Okay, next let's simplify this term. It's pretty close. Next we can forget about the geometry. We just use the numerical data. So here let's recall. So transformation x is xuv, y is yuv. So this is transformation t. For this moment, we forget about the region. So we forget about that. Later on, we will combine previous discussion and the current one. And then So gamma just, what is gamma? Gamma just the same notation for xy coordinates. You just put them together as a vector in the vector form. Okay, then so we can compute the cross product by the cross product formula, ijk, partial x, partial u, partial x, partial y, partial u. And since you don't have 0 as your z coordinates, you put a 0 here, and x, partial v, partial y, partial v, 0. And finally, it's k, partial x, partial u, partial y, partial v, u, partial x, partial v, partial y, partial v. Okay, and therefore, if you take the norm, because k is a unit vector, so you have this. But of course, this you need to take absolute value for this guy. Okay, as we introduced last time, I don't know if you still remember, we have notation for this one. We denote it by partial x, y, partial u, v, and then you take the norm. And therefore, the area of the curved one proximity equals to absolute value of the Jacobian partial x, partial y, partial u, partial x, x, y, partial u, v times du, dv. So this is infinitesimally. So globally, what do you have? Suppose you have an integration of f over region R. Then you can cut it into small pieces. The integral is approximately equal to the Riemann sum. And then for each small piece, we use above discussion. Then you have f, g, u, I, v, j, h, u, I, v, j correspondingly times the area. Sorry. This is sloppy, but we meant is we take a value at u, I, v, j, this point, and then dot du, I, dv, j. And then the last one, we can read it back as integral. So this will be integration of f g u v h u v partial x y partial u v du dv. So this is absolute value symbol. Okay, and here you have extra factor, this one. And the region is, so let's remark, S is the image of R. In principally we know how to figure out S, but for individual problems you need to work a little bit. And the remark, Okay, so let me rewrite the formula again. So the integration of f over r in xy coordinates equals integration of xuv yuv absolute value partial xy partial uv du dv. So this is our formula. And the remark is always take the absolute value of the Jacobian partial xy partial uv. It should be true for even for polar coordinates, spherical coordinates, but if you still remember that for that case, for those cases, those extra factors automatically non-negative because of our choice of the domain for either rho theta or r phi theta or r theta h, because we already choose the domain. Here you might have different choices of the domain, and on different pieces you may have different signs, but we need to make sure the area is always positive. The function can be negative, but the area is always positive. Therefore, you need to take absolute value symbol for the Jacobian here. Okay, so don't forget about the Jacobian symbol, or the absolute value symbol. And an easy example is we can work out the polar coordinate. This polar coordinate. Theta is partial x, partial r, partial y, partial r, partial x, partial theta, partial y, partial theta. And this equals to cosine theta, sine theta, negative r sine theta, r cosine theta. And then you compute it, you get this is r. Therefore, you recall the well-known formula we derived before. The integration of f over r in xy coordinates equals to integration of f r cosine theta r sine theta times r d theta over the domain S. Yeah, another example is for the spherical coordinate. Actually, we already computed last time, so I won't repeat it for you. Okay, next let's look at some some problems. So first, let's look at the example. Use the change of variables. X equals u square minus v square, y equals 2uv, to evaluate the integral of y over the domain R, where R is the region bounded by the axis and the paraboloid y squared equals 4 minus 4x and y squared equals 4 plus 4x. The y positive, 4y positive. Okay, if you draw the picture, it's easily to find. This is what we had for the first example. It's here, so it's here, and therefore we can determine its image. Sorry, it's pre-image. Because remember what we have is you have UV here. So we call UV here. So the transformation is go this way, but then the formula goes the reverse way. That means the integral of f here can be computed by some other function in the pre-image s and dA prime. Yeah, this is a little bit tricky part. So you image go this way, but then the integral, usually we use this side to compute this side, right hand side to compute left hand side. Okay, and then you can determine piece by piece, the same as before, the inverse image of the this one. So just like the first case. Oh, so my bad. So you have red one, yellow one, blue one. So here I will show you how to do this transformation, because a little bit tricky, not tricky, a little bit different. Determine the pre-image. Let's call this as R. This as pre-image of R, or the corresponding S for the R. And the idea is still similar. We map boundary to boundary and figure out the corresponding boundary, and then look at the red one. So what's the parametric equation for red one? So let's see. Left hand side, so this is right hand side, data in R, data in S. So the red one parameterized by y equals 0, x is between -1 and 0. And what is the red one here? Because y equals 0 is 2uv, so 2uv equals 0, and the u squared minus v squared is less than 0 and greater than -1. Okay, then solve it. What do you have? So from the first one, you have two solutions, u equals 0 or v equals 0. So if v equals 0, then -1 less than or equal to u squared less than or equal to 0. You only have a single point, so you omit that. You don't, so let me choose. You don't want this one, there you choose if u equals 0, this is good, and then what you have is, so your v is between 0 and 1, so v is between -1 and 1. You will see here we have a little bit tricky part because we have two p's for one boundary. I can draw the picture here. Let me draw it here. So in the UV plane, okay, and then the red one is given by this. -1, 0, -1, 0. Okay, next let's look at the yellow one. So the yellow one on the left hand side is parameterized by what's that? Y square. So remember, sorry, yellow one is still v equals 0, but then u is between 0 and 1. Therefore, on this side, you have v equals 0. So, oh, sorry, my bad. It's y equals 0. X is between. So because y is 2uv, so 2uv equals 0, u squared minus v squared less than 1 and greater or equal to 0. And then similarly, you solve it, you find your solution curve is u equals 0 and v is between 1, v is 0, u is between 1 and -1. Oh, sorry. So here, for the red one, I made a mistake. Sorry about that. So for the red one, you should have this one, because the solution you have is u equals 0, and the v is between 1 and -1. And then for the yellow, you have this 1, 0, -1, 0. Okay, then let's look at the blue one. So the blue line on the left-hand side, a blue curve, is given by y squared equals 4 minus 4x. And then on the right-hand side, you plug in 2uv squared equals 4 minus 4u squared minus u squared minus v squared. So 4u squared minus 1 equals v squared plus 1 equals 0. So u is positive or -1. Therefore, actually, you have two p's. As before, I would like to do a solid line and dash line check here to indicate which we finally want. So far, you cannot decide which part you want, but later on you can figure out. Okay, now let's do the colorful line, this color one. So this is given by u squared equals 4 plus 4x, and then on this side, color one is 2uv squared equals 4 minus 4u squared minus v squared. So 4u squared plus 1v squared. V squared minus 1 equals 0. So v is positive or negative 1. Therefore, you have okay, so here actually you should do okay, next let's test one point. Suppose you take a point here. Which point? You can take a point in the xy plane and then do the reverse transformation, or you pick a point here and then do the to the transformation, direct transformation. Okay, so I will pick a point, for example, like here, E, 1/2, 1/2, and as we computed before, so T 1/2, 1/2 is given by X is 1/2 square minus 1/2 square, Y is 2 times 1/2 times 1/2, and this is 1/2, this is 0. Okay, so the image is here, T, E. Okay, therefore the piece we are going to choose is this one. Because no matter how, you need to connect the red one. You have red one as a boundary, followed by yellow one, blue one, colorful one. So you might have a question why we choose a point in the first quadrant. So just a small trick. Remark. Check the first quadrant first. First quadrant has a priority because usually the problem will be set up nicely. It's not true for the problem you had in reality, but you have high possibility to have this hold for the test. Okay, then you figure out the domain. Now you only need to integration on this cube. So the remaining stuff is to compute the Jacobian. This part is easy. So recall x is so u squared minus v squared, y is 2uv. Therefore here, partial x, let's write partial x, partial u, partial y, partial u. Partial x, partial v, partial y, partial v. So 2u, 2v, minus 2v, and 2u. So the answer is 4u squared plus v squared. Of course, this is non-negative. And then the integration of y over r is transformed integration over s, 2uv. This is because y is 2uv. And times the Jacobian. Yeah, I would like to write it down step by step. And then the domain is 0, 1 to 1, 0 to 1, 0 to 1, 2uv, 4u squared plus v squared, du dv. Okay, and then the remaining part is easy. You just have quite a standard double integral over standard rectangle domain. So I will omit the computation. It's 2. Okay, let's do one more example without giving the transformation directly. So suppose you have such a domain. So I should say in general, there's no standard rule to have transformation guarantee your integral can be largely simplified. We only have this true for special cases. So it's good to, for the test, I mean, it's good to have some feeling, do some exercise, figure out what is a stereotype for this kind of problems. In reality, you need to use mathematics or MATLAB and Python or whatever, C++, whatever thing to do it. So where R is the trapezoidal region with vertices. R equals with vertices 1, 0, 2, 0, 0, negative 2, 0, negative 1. So before we do actual calculation, we make a remark. So think about in 1D, suppose you have cosine x cubed times x squared dx. So what's your strategy to compute it? You set u equals to x cubed because you want to simplify the most complicated functions, right? And the same idea here. So here, this index is a little bit confusing. So you want to simplify a little bit. And the transformation we like the best is a linear transformation. So that leads us to the following setup, following guessing of the transformation. So set, it might not work, but you have to try. So set u equals x plus y, v equals x minus y. Remember here we reverse the place of u and the v. So under this notation, so you can do it, do the transformation direct. You can compute the image directly without doing it reversely. The best way to figure out this, not to remember the formula, but draw the pictures, and then remember your job is to transform the integral you have to the other side. So no matter what the other side is, no matter what the rule is, you just follow it to figure out the picture. So let's step by step. Okay, and then what you have now is the region in xy plane. So you have 1, 0, 2, 0, 0, negative 1, 0, negative 2. Okay, then let's denote this point as A, B, C, D. And then we need to figure out what is the corresponding picture in U and V. If you don't know it's an image or inverse image, you just say it's corresponding picture. You know what does it mean. Okay, then since xy is 1, 0, what is the corresponding UV? So you just, because the data you have is on this side, so you just plug in, and then so let's see. A10 on this side corresponding to U. U is 1 plus 0 is 1. V is 1 minus 0 is 1. So therefore here you have this point as A prime. And on this side, suppose you have B, then here you have U equals 2, V equals 2. So you have B prime here, and C 0, negative 1. So u is negative 1, v is 1. Here, d is 0, negative 2. U is negative 2, V is 2. Okay, then you connect them together. The corresponding region in, let's call this as R, this is S. Region in UV plane is this trapezoidal region. And if you know that, you can view it as so certain type domain. We will figure out later. Okay, next, you can view it as type 2 actually. You can project down to V. Okay, then we are done with the region part. Then step 2, we always split the problem into 2 parts. First, figure out the region. Secondly, you figure out the actual factor. So because we want to know partial xy, partial uv, so here we have 2 methods to compute it. So method 1, solve, because we have uv in xy, solve xy in terms of uv. You can do that. This is a linear equation. You have this one, and then you compute this partial x, partial v, partial y, partial v. So it's 1/2, 1/2, 1/2, negative 1/2, which is negative 1/2. Okay, so here your okay, so we will leave the last calculation to the last step. And then here method 2, I just claim I will not prove this. You can prove this by yourself. Inverse. So here, what does this mean? So right hand side, you view uv as function of x and y. Because they are related, points are corresponding to each other one by one. So you can solve this reversely, and then you have this formula. Therefore here, you only need to compute the inverse partial u, partial x, partial u, partial v, partial x, partial u, partial y, partial v, partial y. So here you have partial u, because then you don't need to solve the inverse function, because u is x plus y, so 1, 1, 1, negative 1, so which is negative, you have inverse here. So you have negative 2 inverse, which is negative 1/2. Okay, probably this formula, a little bit remark about the formula before we proceed. The formula is well known in 1D. So because in 1D, suppose you have, so y is fx, and you can solve it. X is gy. So partial y, partial x is partial x partial y inverse. Yeah, the notation not that good, but I think you understand the idea. This can be generalized to higher dimensions, and even the Jacobian even satisfied the chain rule. We will discuss this further if we have problems later. Okay, now we can calculate the integral we want to understand originally, and everything you can transform smoothly to u over v. And recall, this is only a trial. We only try this transformation. It might not work, but you have to try. And let's see what do we have. And here, because we project down to v, so we can do this transformation. Recall the boundary is given by u equals v, u equals negative v. So, okay, so here you can have this one, uv times 1/2. Don't forget absolute value here, du. Okay, then for u integral, it's just standard exponential function. So you have 1 to 2 v times 1/2 exponential u over v, u minus v dv, and then 2 to 1 v times 1/2 exponential minus exponential negative 1 dv. Okay, so finally you have v squared over 2 to 1 times 1/2 e minus negative 1. So 3/4 e minus e negative 1. The answer is straightforward. We don't use actual techniques. Okay, I will stop here for this lecture.